Hi, I am Antonio Jose and I will be presenting this performance evaluation for very long baseline interferometry correlation of high-performance computing cloud architectures. The other two authors are Rafael Pastor and Agustín Caminero. I will start with an introduction, then I will show a comparison of different correlators, I will show some benchmarking results, and I will finish with some conclusions. Well, very long baseline interferometry is a radio astronomy technique that basically combines signals from different radio telescopes that are pointing towards the same astronomical source, and they achieve an improvement in resolution. And nowadays this processing is mostly done via software, and it uses signal processing and high performance computing. And the main applications of this technique are imaging. For example, they took an image of a black hole using this technique, and geodesy. Well, if we look at the evolution of these systems, we can see that they started developing hardware, like application-specific integrated circuits, as the Mark IV, which was developed by MIT Haystack. Then they started changing for software, and we have defects. And there has also been some attempts for running correlation using specific hardware like GPUs, and nowadays they are trying to run this correlation on the cloud. So we have correlators which were born to run on the cloud. For example, Correlix, which is based on Apache Hadoop, or CXS338, which is based on Apache Spark. And if we look at the trends on the technologies for parallel processing, we can see that there's an ongoing change from the traditional approach, which is C++ and MPI, which achieves very high performance, towards a big data oriented approach, which is more focused on scalability and ultimately on performance too. And this basically uses frameworks like Apache Hadoop or Apache Spark, which is a framework which is part of this framework and promises like 100 times the performance that Hadoop provides. What we have in this slide three correlators that we mentioned earlier, which are Defects Correlix and CXS338. Defects is written in C++ and is based on MPI, whereas Correlix and CXS are based on the Apache Hadoop framework, and CXS is based on Apache Spark. And if we look at the development times of these projects, we can see that Defects is a project that started back in 2005, and it's production grade and it's used worldwide nowadays. On the other hand, Correlix was a 2-year development effort and is currently discontinued. And we have CXS338, which has been developed in 4 or 5 months. In this slide, we try to provide a qualitative comparison between these three correlators. So we have Defects, the de facto standard, Correlix, we will call it the legacy system because CXS338 is a fork of this project, and CXS338. So we can see that Defects provides the highest performance. It can be considered the standard because it is widely used, it is the standard processing chain. But the other two projects were born to be run on a big data oriented framework. The architecture is also simpler, and they have a permissive license, which is an MIT license. So in the following slides, we will be presenting some benchmarking results comparing Defects and CXS338. In order to do this, we took the most recent reference presenting benchmarking results for Defects, and we tried to follow their methodology and repeat the experiments with the CXS338. We will refer to the reference experiment as the baseline, and in this experiment they use 20 GB per station, and the parameters that can be seen in this slide. And there is one important difference between the original experiment and the proposed experiment, and that is that in the reference they have done vertical scaling on a high performance machine, and we will be doing horizontal scaling on modest machines. In this slide we can see the scalability results for an experiment that took 2 stations, and we can see that for the baseline experiment they have scalability up to like what they test, which is 96 virtual CPUs. And in the case of CXS338, the curve is closer to the asymptote, but it starts scaling at a point which basically depends on the number of natural partitions. And this number of partitions basically depends on the number of accumulation windows and the number of frequency channels. And that is that way because CXS338 doesn't have like micro optimizations like defects, which has a feature which is the subaccumulations, and they allow to continue scaling beyond this natural limit. In this slide we can see a performance comparison between the 2 systems. We can see defects on top and CXS338 at the bottom. And we basically selected the parameters so that the cluster for CXS had the same number of virtual CPUs as defects for this case. So we can see that we have 16 CPUs in both cases. And regarding memory, the cluster used in the reference has like double the memory that the cluster used for CXS. And the performance result is also more or less half. So we have defects with roughly 20 megabytes per second and CXS with roughly 10 megabytes per second. And it is worth mentioning that in the CXS cluster, half of the virtual CPUs were underused, basically for a lack of memory. So we would expect an improvement in performance if the cluster had more memory. In this slide we compare some parameters between the baseline and the CXS experiment. Well, we can see that the providers are different. For the reference they used the Google Cloud Platform, whereas for CXS we used Amazon Web Services. The instance types are also different. For defects they used a very high performance machine, whereas we used modest machines. The processors are similar, that's why it is possible to more or less compare performance per virtual CPU. And the memory is also quite different. So in summary, we have shown that CXS achieves like half the performance of defects in the worst case. And we have also validated these results with unit tests, comparing the results of CXS and CoreLX. And the validation between CoreLX and defects can be seen at the CoreLX repository. And it is worth mentioning again that only half of the total CPU cores were used due to memory limitations. In terms of lines of future work, Apache Spark comes with a feature which allows basically streaming, so it would be possible to do real-time correlation. For example, integrating Apache Spark with Apache Kafka infrastructure for memory passing, for message passing. It would be also interesting to work on the memory usage to basically improve performance, and it would be also interesting to work on micro optimizations like the subaccumulation windows that we mentioned earlier, that would allow an increase in the scalability. And this is all. Thank you for your attention.